Hello, my name is Rolf Bergman, and this is Chapter 2, Training for Certified Senior UV-C Technician that NALCO has defined. This chapter is concerned with germicidal UV-C lamps. This training is also a prerequisite for the management professional interested in UV. Next slide. The goals for this chapter is to describe lamps that emit in the UVC region, particularly those used for air and surface disinfection. And also, we will describe lamps that emit in the UVC region that are not used for air and surface disinfection, but these will not be treated in quite the detail. We also want to show the similarities that exist between the lamps that emit in UVC and the lamps that emit in visible region, in other words, ordinary lamps of various kinds. We also want to understand how UVC is potentially harmful, so that lamps that emit in the UVC region need care and control, and they need to be shielded from human exposure, at least above a certain level. So the objective for you, hopefully, is that you will be able to name the different types of lamps that are used in germicidal UV air and surface applications, and that you recognize the lamp type by looking at it. So going on then to the main portion of this section, the overview is that we will look at low pressure mercury lamps. Mercury has Hg as the name for mercury. We will look at excimer lamps, particularly one kind of excimer called krypton chloride. Those are the two gases that are mixed together to create the discharge. We'll look at LED lamps, light-emitting diodes that can emit in the UVC region. And then, as mentioned, there are two other types of germicidal lamps that are used, but used differently and not usually for air or surface disinfection. These are medium pressure mercury lamps. They will be used mostly in water purification or food disinfection. Also, xenon arc lamps, particularly pulsed kinds, have a very broad spectrum going all the way through the UVC, but they also emit in the UVB, the UVA, and the visible and IR region. So these lamps cover all the regions. They are not often used, but can be used for air disinfection, but not with people present. Next slide. We'll then start with low pressure mercury lamps. This is the classical germicidal lamp. In fact, you can see that there was a patent issued for this kind of application of a low pressure mercury lamp way back in 1886. This is about the time that Edison was developing the incandescent lamp. So you see it goes a long way back. Now, low pressure mercury lamps look identical to regular fluorescent lamps. There's a picture here of a Philips T8 lamp. The difference between the fluorescent and the low pressure mercury lamps for used in the UV is that there's no phosphor on the inside surface. The phosphor actually does the converting of the 254 line, which is a major emission line, and creates visible light. And the ordinary glass that's used in lamps do not transmit ultraviolet in the UVC region. So in order to get UVC out, we need a special glass. It looks the same as regular glass, but it has different properties. And just like other fluorescent lamps, it comes in various diameters in various lengths. In linear shapes, they can go from about 4 inches long, 8 inches long to 3 foot long, but they can also be bent. They can made into a kind of what was used for CFL. And so all of these forms can be used. So whatever we can make a fluorescent lamp for, we can make the special glass lamp. The electronics that drive the germicidal version and the one that drives the regular fluorescents are really not very different. For very small diameter lamps, it is difficult to put a coiled heated cathode in. So for these lamps, they are called cold cathodes. Shown is a picture on the right. It's a little difficult, but at the top you can see the cathodes. I'm sorry. And they emit their little tube at the ends. They are not, they can have some emission mix on them, but they're used for the smaller tubes. Next slide, the UV and visible spectra of a low pressure mercury lamp is shown here below. We show the irradiance in actually watts per meter squared. And you notice that there is a very large emission at 254 actually, which goes all the way up to 2. And then there's a number of smaller emission peaks in the UV, and then above 400, which is where the visible starts. Now you can see all the way up to 600, there are small peaks. Now it turns out that spectrometers can measure over many orders of magnitude, so we can look at these smaller peaks and see actually how they look at. And we do this by making a logarithmic graph. In other words, rather than having a linear scale on the vertical axis, we have a logarithmic scale. And this is shown in this slide. And notice now that we're looking at many orders of magnitude. We still see that we have at the peak of this at 2 times 2 watts per meter squared, but we can look all the way down to 10 to the minus 6 watts per meter squared. So we're looking at 6 orders of magnitude over which the spectrometer can sense signal. And it looks a lot more complicated, but the 254 dominates as before, but we also see that the other visible lines or UV lines are present as well as in the visible region. Mercury in the visible region emits at 404, 436, 536, 577. Those are the major lines. And as well as emitting as we get into the visible. They also emit in the UV B region in particular. You see a line at 303 and at 365 are the 2 main lines. Notice also that the peak of these lines is about 2 orders of magnitude below the peak of the 254. To show you how this compares when we look at the spectra of a linear lamp, I show that in this slide. The green line here is the same as the line before, except I now only go to 450 nanometers. I don't go all the way through the visible. And you notice the red line is a GE F8 1-inch lamp with a special phosphor called cool white. But the important region to look at is the transmission in the UVB region. You notice that at about 320 nanometers, the red line goes away, going away by the time you get to about 290. So that's the cutoff of the regular glass, which does not allow the UVC to be emitted. Otherwise, you see the spectra look very similar. And even in the absorption of the glass, you can see some of the lines come out at 290 and 303. So this for comparison, and then the red line phosphor begins above. You can see a little bit of an effect above 400, but most of it takes effect at higher regions, not shown. So why do we use low pressure mercury lamps for germicidal applications? Well, they're very efficient. You noticed from the first slide that almost all the light came out at one line in 254. It's not exactly at 254, it's 253.7, but it is a lot of the emission of the mercury spectrum is at that line. And more than half of the input power is actually emitted at 254 nanometers. We can talk about a half, but it actually depends on the length of the lamp and the diameter of the lamp and so forth. So for long linear lamps, it's more than half. As you go to shorter lengths, that fraction of the power goes down. So the special glass that is used cuts off any ozone generated at lower. There is a mercury line at 185, which is about 10%. It's the second strongest line, and that's completely absorbed by the special glass because it would create ozone. So, but the glass that's used, it doesn't transmit 100%. It transmits only about 85%. So we're already absorbing a little bit of the 253.7 nanometer light that is coming out, and about 85% is pretty good. However, that fraction goes down with time as you burn the lamp for various processes. So that makes a useful life of about 10,000 hours. The other reason that they've been available a long time, ever since you've been making fluorescent lamps, the technology is there to make these kind of lamps. You do have to make the special glass tubing, but that makes them easy to operate and relatively inexpensive to buy. So for these reasons, this lamp, and because it has been used historically for a long time, it is still the major lamp used in the industry for germicidal application. So we shift then in this slide to excimer lamps. These are relatively new on the market. Excimer lamps have been around for a while, but not necessarily used for germicidal applications. That's and it's still because they operate in a region of the ultraviolet spectrum called the far UV and below 230 nanometers. That their use has not been explored as well as, for example, the low pressure mercury. But this is changing because there are benefits from using the far UV, as you will see. What is an excimer discharge? Well, it's a special kind of gas in a discharge gas where you get two of the atoms, for example, chlorine and krypton, are become in an excited state, and they form a dimer. In other words, a molecule held together, but they're held together only in an excited state. And when they emit a photon in dissociating back to their normal neutral atomic state. So these dimers only exist during the discharge when they can be created by electron bombardment in a gas discharge. They can be created out of many different combinations. All the rare gases, helium, neon, argon, krypton, and xenon will form dimers, not very efficiently for most cases, except for xenon, which forms a dimer that is very, very large in number. but we can add halogen, fluorine, chlorine, bromine, and iodine to the gas. Much smaller amounts of the halogens are added, but then the atomic elements actually combine, so we get a xenon chlorine, for example, or krypton bromide. If we mix these two gases, we get emission, and because the dimer holding energy is different when they emit a photon, by disassociating that photon is at a different wavelength in the spectra. It has different energy. A particular use in germicidal application, the UVC region above 200, there are two exomers that have been studied. Krypton chlorine exomer, which emits largely at 222, and krypton bromide, which emits at 207. Because the 207 is near the edge of the UV and also creates quite a bit of ozone, it is not used extensively in the industry. So mostly krypton chloride lamps are what is being manufactured and made available for germicidal applications. So now, because they have halogen gases in there, you cannot put metal electrodes inside the gas. Any kind of electrode sealed in the end of the lamp would be eaten up by the chlorine or any of the halogen in fast order. So they have to be, the discharge has to be created differently. So this is done by pulsing a lamp through a metal on one side of the lamp and a metal on the other side, a cathode and an anode, or the gas is in between. And this is called a capacitive discharge. And the high voltage is needed to create a discharge. When the voltage is enough across the electrodes to break down the gas, you get a large current spike. But because the charge is limited due to the capacitor of the glass, it only lasts a few microseconds. So the drivers for exomer lamps therefore provide very high frequency pulses of a few thousand volts minimum. And so they are driven, the pulse rate is on the order of 50 to 100 kilohertz, 50 to 100,000 hertz, so very high frequency. However, the way the electrodes are placed can vary quite a bit, so the configurations of the discharge can vary significantly. This is shown, we'll show some examples here. This is a very popular use of a small tube that you can see on the right, and there are electrodes here are placed side by side. One at the top, which is a metal that is folded around the lamp. There are actually more than one lamp, and then a piece of metal at the bottom, also made to go around different lamps. And you see that the white is actually the arc discharge between the cathode and the anode because the space in between changes from positive to negative. So this kind of lamp the lamp is only about 1/8 of an inch in diameter and about 3-4 inches long. They're packaged together in 4 lamps. Ushio makes this. However, there are other kinds of configurations and which create much more power. Here we have a metal which is in the center, a metal ring, which is one electrode, and then a kind of a donut-shaped glass holding the gas is put around that metal, and then over the top is the other electrode, which is like a grid that covers the whole glass, and it's a grid so that the light can come through it. And so again, you have a pulse between this one, then goes directly out from the center to the edge, and the light generated comes out from the whole tube. So these kind of lamps have also been used, and they create a discharge which has the same spectral shape, more or less, but much different power capability. These kind of tubes can create 100 to 300 watts of power, much more than the 10 to 20 watts that the previous example showed. I show here a spectra of a krypton chloride excimer lamp. Actually, the one generated, the spectra is generated from the 4-lamp Ushio CARE 222 model. The blue line shows the now logarithmic spectra again. This time we don't put units on there, but it's normalized to 1. But you notice that there's a peak at 222, but then there is a little subsidiary excitation about 235 and at 259. And then it also has some emission in the UV B and A region, although it seems it's more than 2 orders of magnitude down. But nevertheless, the 259 peak, even though it's only 1%, maybe 1.5%, and the UV B region, which is broadband, and therefore the energy in between 280 and 315 nanometers is significant. So what was found is that if the lamps as used will create sunburn or with overexposure, even though the 222 is not responsible for this. So the need was seen to provide a way to filter out the higher wavelengths above 240. So you see then that a filter was developed that is placed over the top of the lamps, and this filter acts to cut down the radiation above 230 by about 1 to 2 orders of magnitude. So 100 times less light coming out in the UV C and B regions above 230. It also has some effect of filtering below the 222. You notice that at 200, there's over an order of magnitude less emission with the filtered lamp than the unfiltered lamp. This is shown here. And that's a benefit in terms of ozone generation, because ozone is generated with increasing strength as we go down in wavelength below 240. So, and particularly in the near 200 nanometers, so the ozone production is reduced significantly by the filter compared to the unfiltered lamp. So 2 benefits. 1, we can use the lamp at higher dose levels with the filter, and there's less risk of too much ozone being generated. The excimer lamps, particularly krypton chloride, are good for, they have an advantage in air disinfection because the skin penetration at 222 nanometers is significantly less than that of 254. Since the skin does not, since the radiation does not penetrate the outer layer of the skin, it does not reach the underlying active layer of the skin that create the sunburn kind of effects or even cancer. So this allows the lamp emission on contact with the human body to be significantly higher than that for 254. And furthermore, the disinfecting capabilities at 222 are as good at, in some cases better, some cases not so good, not as good, but they disinfect the organisms or viruses, microorganisms in the air. So you have the capability now of having safe irradiation that is also effective enough in disinfecting organisms to be of real help. This is not possible with lamps that emit higher wavelengths, like the low pressure mercury. I should mention that in the picture you can see an example above the speaker of a 222 unit put on a pole, and over on the other side you can see an example of also on a fixture of a low pressure mercury lamp, which is now put in a band. It's filtered so that it only radiates above the heads of the people. So whereas the 222 unit pictured can radiate over and effectively that radiation can be with people present. We mentioned ozone generations. It has been concerned that ozone in itself is probably not so big of an issue because the amount generated is not so high. But volatile organic compounds called VOCs can interact with the ozone, and it was potentially thought that this could create small particles that are not so good for health. The solution is obviously that we need ventilation to control the levels of ozone, so it is not recommended that the 222 be used in situations where there is no or very little ventilation. And furthermore, so that controls not only the ozone, but also the volatile organic compounds. And if the air is going into the room is filtered, that further removes the volatile organic compounds. The data to date seem to indicate that, yes, you can measure these levels, but we don't believe they are the generation of volatile organic compounds by the level of ozone generated is significantly harmful, but more data is needed and will be forthcoming. How efficient are krypton chloride lamps? Well, they're very inefficient, actually. The actual output in the 222 band is about 1% of the input power. And the input power of most of the 4 lamp units range from 10 to 20 watts. The cylindrical type lamps are much more efficient, and you can get about 10% output out of 100 to 300 watts. The difficulty is that that's actually too much ultraviolet power and difficult to control. So we mentioned a little bit about the disinfecting capability of 222 nanometer emission versus that of low pressure mercury at 254. And for viruses in air, especially if the air is dry, the 222 is actually more effective. And but it is not as effective for bacteria. And the reason is, it probably is the 222 penetration depth is not deep enough to get through the bacterial assembly to reach the, to actually kill it. On surfaces, 222 is shown is probably not as effective, but it varies a lot compared to 254, again, for the same reason. On the surface, the viruses are covered usually with other kinds of material, very small films of things that are there, and the 222 cannot effectively go through those films and reach the virus and therefore inactivate it. But the results vary significantly depending on what kind of surfaces, what kind of material is used. And a lot of study is still going on to determine the trade-offs. Okay, so much for krypton chloride or excimer lamps. Another type of lamp that is being developed, and probably the newest one on the market, is the light-emitting diode. These are being developed in the UVC region. They've obviously taken over the visible light market. It's hard to find all the historically known lamps. Now almost everything is an LED. But the development of LED, and they are used in the UVA region, are very effective. But in the UVC region, they are still under development because the efficiency is very low. And even, say, below 250, they are extremely low efficiency. But things are changing rapidly. So the current status is that in the very upper region of the UVC region, from 265 to 280 nanometers, the efficiency is currently about 10%. But notice as we go down to 250 to 265, this is the region where you have comparable light emission as low pressure mercury, which is at 254. It's already dropped to the order of 1%. And below 240, in the region of the 222 or 230, where we'd like to work for the far UV, to compare it to the krypton chloride excimer lamp, the efficiency is 10 times lower again, only 0.1%. And compare that, for example, with emission in the visible or the UVA region, where it's 95% or higher. But there are breakthroughs, and some of these have happened recently, and breakthroughs in materials, and aluminum, indium, nitrogen materials are being developed that provide a better material for particularly the far UV. And so I think companies are looking at this to see what is possible. So there is a lot of development going on, and it's changing rapidly. Currently, as shown in this slide, you see that the efficiency in the as I mentioned before, about 10% in the upper UVC region, right next to the UVB region, is on the order of 10%. But by the time you get down to 222, it's very small. The shortest UVC lamp emission that at least I know of, and it may have changed by now, is on the order of 210 nanometer. So the potential is there to go down that far in wavelength. But while UVC emits in a fairly small wavelength region, nevertheless, it is not a line emitter. It is a band emitter. And so one of the things one has to be careful is the upper band. And shown here, you see if you have an LED at 270 nanometers, the long wavelength tail, about 10% of that emission is about 280, and even some emission all the way up to close to 300 nanometers. This is a linear scale. And so that above 280, you're in the UVB region, and the skin penetration of radiation is much deeper. The penetration grows very rapidly around 270, 280. That's why the 280 is the breakoff region between UVB and UVC. So that even though there's not a whole lot of radiation above 280 in terms of effects on the body, it is very significant. So care needs to be taken. And so what should not be done is for application, direct application for on people where people are present, so that the emission enshrouds them, so to speak. The peak wavelength, I would think, would need to be at 260 or lower. UVCs have some significant advantages, and It's all in one direction. The other devices that we showed, low pressure mercury and the krypton chloride lamps, are kind of isotropic emitters. They emit in all directions from the tube, and in almost all cases, we want the UVC that we have to be emitted in one direction. In fact, to be channeled into a beam in many cases, sometimes to be not to be distributed overall, but all in one direction, not in two directions. So, but you can easily focus even the emission in one direction by adding small optical elements, and you can also spread the emission if so choose. And and furthermore, an LED in the UV and an LED in the visible more or less requires the same kind of structure and building and put on board, so that the combination is much easier to do with LEDs. I show an example here of a prototype developed by GE Current. There's an LED in the very center, just barely see it behind, and then there's a reflector that spreads the light so that the light actually comes out at 80 to 90 degrees. And if this is mounted in the ceiling, then most of the light generated by the UV LED is above the heads of the people. So it's effectively out of direct contact. I will finish by going through the two other kinds of discharge lamps that we discussed that are used for germicidal applications, but not in air and even for surfaces. First one of these is medium pressure mercury. The reason this is used is that it's a lamp that provides a much higher power. Medium pressure mercury lamps just look like HID lamps, just like fluorescent lamps, or low pressure mercury germicidal lamps look like regular fluorescent lamps. The lamps here are made out of quartz, sometimes doped a little bit to make it ozone free. And but they use a molybdenum foil seal. You can see that on the very right of this picture, the foil seal. And then there's an electrode inside. This time not a coiled electrode, but a pin or button electrode. And the mercury dose is put in a measured quantity so that you have so much mercury per unit for the volume of the lamp. And then you run the discharge high enough that the mercury, that the walls get much hotter than they do in a fluorescent lamp. In a fluorescent lamp, the power is limited so that you don't so that the surface temperature of the lamp is only in the region of 50 Celsius, only 20 degrees above room temperature. But in a medium pressure lamp, you put enough power in the lamp that the lamp heats up and all the mercury evaporates. So you have a much higher vapor pressure of mercury, and on the order of 1 atmosphere now of mercury in the lamp. And what happens is then that the power per unit length in a medium pressure mercury lamp is on the order of 200 times higher than that in a fluorescent lamp. So the volts per inch, it's about 1 volt per centimeter in a regular fluorescent lamp, whereas 200 volts per centimeter in a medium pressure lamp. It's also developed a long time ago. Heraeus is still in business. They operate in Europe. So 1904, long time ago. Because of the very high power nature of the lamp, you usually have things that go from 400 to 60,000 watts, depending on how long you make the lamp. And these are used then for in waterways for purifying the water, drinking water for cities. And by the way, low pressure mercury lamps can also be used similarly, and are used also for water purification. So both types of mercury lamps are used depending on how much power is needed, what's the water throughput, and so forth. Also for food disinfection, medium pressure mercury lamps are used. And these are in chains of produce, for example, that you need to disinfect the produce before it goes to market, between the farm and the market. So what happens, though, as you increase the mercury line is that the very big piece in the UVC, the 253.7 line, now it's still there, but it gets reabsorbed by the gas, and so the emission spreads to other regions. So there's a large increase in UVB emission, as well as some increase in the visible emission. And the 253 emission is reduced from so that there's only, instead of on the order of 50 to 60, only 15% of the power at max is effective for germicidal applications. But because you can put a lot more power in, as I said, 200 times more power than a fluorescent lamp for the same length, the total power, UVC power generated is much higher, and therefore that is a benefit. You can also modify the gas filling, the doping, and the quartz to tailor to specific situations. I mentioned this spectra before. Notice now that in a linear scale, the emission at 254 is actually almost gone. It's self-reversed, and it pushes radiation out in the UVB and the UVC region. So now the strongest line is actually 365 in this particular case. It varies, but notice that even for water and those kind of things, emission in well, not 365, but 300 and 310 are effective germicidal. So medium pressure mercury lamps are effective for that application. Secondly, and finally, we will talk about xenon arc lamps. I show an example here of a DC arc lamp, a very short arc gap in very high pressure. They can also be all kinds of things. Most of you have seen the flash lamps on poles that for warnings to air. These are all xenon flash lamps mostly. They have long life. They're only filled with xenon at various pressure, although they can be filled with xenon mercury. They can be short variety, long variety, and they can run in continuous mode, or they can be pulsed. And pulsed lamps are used for germicidal application because the spectrum in the UVC region becomes enhanced very much compared to continuous wave operation. But as mentioned before, whether pulsed or not pulsed, the emission is all the way through the UV and the visible spectrum. So this makes it great for sources for doing spectroscopy as a light source for spectroscopy, but it can't be used for direct application with people present. Here's an example of the spectra, and you see the difference, very large difference between continuous and pulsed wave. By the way, the picture is of an AC arc, but in a very large power bulb. So all kinds of configurations again. So the conclusion is we've talked about 5 types of lamps that emit in the UVC region: low pressure mercury, excimer, and LEDs. Those on the left are used for air and surface disinfection. Medium pressure mercury and xenon on the right are specialty applications. Medium pressure mercury being used for water and food processing in large bulk situations. They must understand too that all of these lamps, any emission in the UVC is harmful if applied above a certain amount, that is in radians times time. We'll talk much about that in another lecture. So depending on the situation and whether people are present, how you put the lamps how you install the lamps and how you maintain this system is very important. We say potentially harmful because in well-installed situations, they are not harmful. Thank you very much.